It's so great to see everybody here. It's so great to see old faces that I haven't seen in a very long time. By the way, I'm Marshall, in case you don't recognize me here, okay? All right, so let us start this whole adventure with an introduction from our president, Farnam Jahanian, 10th president of Carnegie Mellon University. And in fact, as a small tidbit, Farnam is a computer scientist, a renowned computer scientist, and as such, he's a fellow faculty member in the School of Computer Science. We'll discuss teaching assignments and things later, Farnam, okay? So please welcome Farnam.
You know, whenever I'm at an event like this, I'm worried that Marshall is going to give my teaching assignment, and he always threatens to do it. It hasn't happened yet. It's good to be with you. It's good to be with our fellow computer scientists, of course. And before I get started, I do want to acknowledge Marshall's exceptional leadership as Dean of our School of Computer Science, but also, of course, as your fellow roboticist, he's had a disproportionate impact, of course, through his leadership of the Robotic Institute and, of course, on outdoor autonomy, which is the topic of this conference. I do want to tell you that years ago, after I came to CMU, I did watch the Scientific American video from 1997 when Marshall and Alan Alda were driving around autonomously. Back then, of course, this was just like unbelievable. But if you haven't seen that video, I encourage you to go see it. Marshall had actually had gray hair. So, I mean, sorry, black hair at the time. So you have aged well, my friend. Anyway, is this being recorded? Okay, great. No problem. We're among friends. To echo Marshall's welcome to all of you. Good afternoon. Welcome to back, those of you who are back visiting Carnegie Mellon, and welcome to this year's Reddy Symposium. To prepare for this event, Marshall and the SCS team, who deserve enormous credit for all the logistics and the work that goes into making these events happen, of course, had a couple of our old friends who helped with the logistics. I don't want to acknowledge Chuck Thorpe and also Tony Stentz, who are back here. Thank you, Chuck and Tony. And as all of you know, Chuck spent 3 decades here at Carnegie Mellon, of course, first as a PhD student, later served as Director of Robotic Institute, and I think you're also in that Alan Alda video, aren't you? I think. Yes, you are. I thought so. And of course, currently serves as president of Clarkson University, but Chuck also had a very successful stint at our CMU Qatar program several years ago. Tony, is Tony here? There you are. Tony is here, and Tony is, of course, CMU alum and long-term roboticist. He, of course, had a successful run directing NREC and very much remains connected to Carnegie Mellon and the Robotic Institute. I do want to thank everybody else who's contributed to organizing this symposium today and tomorrow. Thank you for all of your work. Appreciate this work. I'm going to try to be brief, but I want to say a couple of things. As Marshall mentioned, not only I have the honor of serving as president of Carnegie Mellon, but also I'm a fellow computer scientist, and I'm very proud to be part of this community. It also means that I have a somewhat of a front row seat and a clear view of the exceptional talent that resides in our computer science school, of course, across all areas, including AI, autonomy, robotics. And while we have some of the brightest minds in computer science with us today, this afternoon also, I know as I spoke to a number of you as I came in, it's a gathering of a bunch of old friends and long-term colleagues who are part of the community that has grown so well and so much over the last few decades. You're all united by your deep understanding of the profound, unprecedented technological advances that are transforming our society, our economy, and of course, culture. Our scholars here continue to advance revolutionary breakthroughs at the intersection of technology and humanity. And we're using these breakthroughs to engage with the world in new ways and to improve human conditions with new solutions in hand. And I know this conference is going to highlight a number of those things. It's against this backdrop that it's impossible to overstate the impact of SCS's leadership, faculty, students, and of course, staff and alumni that have had not only our own community on Carnegie Mellon, but also on society. And to the extent that the SCS's contribution has strengthened Carnegie Mellon's global impact, our reputation, and reach, and I mean globally. CMU, and especially our computer science colleagues, have played a disproportionate role and a pioneering role in bringing about the digital revolution. And by the way, you've been able to achieve this impact because you, all of you, have been relentless in pursuing and nurturing and pursuing actually research and development across the spectrum of areas. But I want to go off script for a second. At the time, we live in a very fractured world. I promise, this is not a political statement, but let me just share something with you. The society has come to question the value of higher education and research. But it's really important to recognize the role of education in catalyzing social mobility, and also the vital role and importance of scientific discovery and engineering innovation to solve some of the most important challenges that humanity faces. As all of you know, discovery and innovation does not happen overnight or in a straight and predictable path. If it did, life would be really easy. In fact, there's often a long, unpredictable incubation period between initial exploration and the long-term impact of discoveries that happen in a scientific lab. This is why sustained investment in research is so vital to the next wave of progress and development that humanity needs. In fact, for this group, consider the benefits that we're seeing from the impact of generative AI, and we're still scratching the surface. But think about decades and decades of investment that has gone into research in AI that has put us in this position. And since I see some of you who were involved in the DARPA Grand Challenge 2007, just imagine the research that led to that and where we are almost 20 years later. So none of this happened on a straight path. None of this happened, in fact, on a predictable path. We also need to, of course, to make concerted effort to take risks, as this group knows how important that is, to fuel discovery at the edges and intersection of disciplines, and CMU does this uniquely well, and our SCS colleagues absolutely know how to do that. This is really what has enabled much of the progress that we have seen that can be attributed to the research in computer science at Carnegie Mellon. Of course, while research strains interact and we see a lot of the progress that happens at the edges and intersection of disciplines. And in fact, much of the progress that you will be talking about today and tomorrow can be seen as a result of essentially advances not only in foundational work, but also advances that have been made at the edges and intersection of different disciplines coming together to amplify the impact. I want to share that with you because I think it's important at a time where the world is so fractured for us not to lose focus that investment in research and education is so important to humanity, and it's so important to human progress, and it's so important to society as a whole. And of course, I'm grateful to all the work that our colleagues in SCS do. I was mentioning this a couple of minutes ago. Usually I would be here for later on this evening for the Reddy lecture seminar and the dinner. It turns out in about 3 hours I'm going to be on a flight to Doha, to Qatar, because our Carnegie Mellon Qatar campus is celebrating its 20th anniversary. So I will not be here tonight to honor Reddy. However, Raj is actually partially responsible for our Qatar campus, so it's his fault that I have to get on this flight, but I'm delighted to be able to go and represent, of course, our colleagues in Doha for the 20th anniversary of our Qatar campus. And as I mentioned, Chuck also played a huge role in that. But I want to take a couple of moments to acknowledge Raj, because I usually would do this later on this evening at dinner, but I might as well take the opportunity, since you've given me the podium, to say a couple of words about Raj and the impact of Raj on not only Carnegie Mellon, but on our discipline and, of course, on the world. You all know that in the long history of groundbreaking achievements that have defined computer science at Carnegie Mellon and our entire campus, very few have been more impactful than our own Reddy through this journey. Raj goes without saying that it's a living legend, a man who has had a front row seat as our technology-enabled future unfolded. By the way, if Raj knew I was going to do this, he wouldn't let me speak today, so let's just get that out of the way. He has, of course, catalyzed significant advances in robotics, in speech recognition, and AI. And he's been the architect of some of the truly historic demonstration of AI's power to enhance humanity. There are many scientific examples of that, and I know you'll talk about some of that today, tomorrow, and of course this evening. But also, Raj has had a disproportionate impact on Carnegie Mellon through his leadership. After joining in 1969, he worked alongside of other legends like Newell, Perlis, and Simon to create Carnegie Mellon's Department of Computer Science. Later on, he helped to establish SCS, which was the first college in the world devoted solely to computer science. Yes, many of our peers 30 years later figured out that was a good idea, but we were way ahead of them. And he served as the founding director, of course, robotics in his institute, and then later on as dean of computer science. He has recruited countless number of professors and students and scholars to Carnegie Mellon, some of you in this room, and secured, of course, support for many, many research projects. He not only founded Robotic Institute, but also the Institute for Software Research, which is now known as S3D. Raj has received many accolades, and of course the Turing Award being with Ed Feigenbaum being one of those, and many other honors, too many to enumerate, but also being a member of National Academy of Engineering and Academy of Arts and Sciences. But on a personal note, I want to tell you that because of Raj's revolutionary work and his impact on CMU, the university conferred on him an honorary degree of Doctor of Science and Technology just a couple of years ago. Conferring honorary degree to our own sitting faculty is extremely rare. In fact, Herb Simon was the other fellow who received that at the time when he served on the faculty. I say this with a great deal of pride that it was and it still is a personal privilege for me to be the one to confer that honorary degree on Raj during our commencement a couple of years ago. Many more things to be said about Raj, but I want to ask you please to join me to recognize Raj. Raj, please stand to be recognized. And thank you for all that you've done for Carnegie Mellon. Just to wrap up, you have an incredible round of panels today and tomorrow devoted to outdoor autonomy, its success at CMU, and of course an opportunity to explore future developments in this area. I encourage all of you to not only to reconnect with old friends, but also to make the most of this remarkable collection of CMU faculty, researchers, alumni, collaborators, and students and friends that are gathered here today and tomorrow. I wish I could be with you today and tomorrow, but I'm going to be on a plane in about the next 3 hours or so. Enjoy the next couple of days, and thank you again for being here. Thanks very much.
Thank you, Farnam. Before we start with the technical panel, let me give you a bit of background about what this symposium series is about. A few years ago, a fund was created in honor of Raj. And using that fund, we are doing every year a symposium on topic that reflects both Raj's contribution and the history of the School of Computer Science and Robotics Institute in particular. We had one celebrating the 50th anniversary of the first speech recognition system at CMU. We had one last year on computer vision and the history of computer vision at CMU. And this year is on outdoor autonomy. So this is the context of what we are doing here. And I join, of course, Farnam in thanking Raj for all he did for the School of Computer Science and for CMU. Thank you. And with that, we're going to start with the first session. I talked about history, so we're going to go way back in history. Yeah, thank you, Chuck. I like to date you a little bit, age you a little bit there. And welcome Chuck Thorpe to the podium. Chuck?
Involved with the NAV lab in some way or another. Stand up. Now you know I'm not going to acknowledge individually everybody who was involved, but this is the group who really put the stake in the ground and said Carnegie Mellon is going to do outdoor mobile robots. Thank you and congratulations. I'm going to give a kind of a personal history here, that I grew up reading Scientific American and looking at the articles on things like robots, and they had pictures of Shaky. Shaky was the robot developed at SRI that could move down a hall indoors and recognize things. It turns out, go ahead and click. Yep, I can click. If I can figure this out. Oh, there we go. Turns out that Shaky worked because there was a 6-inch black baseboard. So the computer vision system was really pretty simple, but it did have a laser scanner. But it's really more about AI than about computer vision. This got me inspired. I was talking to my psychology professor. I said, I'm interested in AI. He said, you should go to Carnegie Mellon. Herb Simon just won the Nobel Prize. So I showed up here 45 years ago. At the immigration course, Raj said he was starting a robotics institute. I signed up to go to work for Raj, and I've been working for him ever since. One of the first hires was Hans Moravec. Hans, in '72, was a student at Stanford, and John McCarthy said, this is in 1972, now that we figured out AI, let's just put a camera on the thing, and then we can figure out robots. Why don't you build a robot car that can go pick people up from the Stanford airport when they're coming to visit us? 10 years later, when Hans finished his thesis, John said, if I'd known it was going to take you 10 years, I wouldn't have funded you. If I'd known nobody else was going to do it, I would have funded you better. Can you click to the video? So Hans, for his thesis, was working on stereo vision, on path planning, and on the predecessor of SLAM, figuring out where he was. And this is why I have an assistant to help run this, because I can't figure it out. His system worked, but it worked very slowly. He would take 9 images, think about them for 15 minutes, move a meter, take another 9 images, think about them for 15 minutes, move a meter. When he ran it outdoors, in those 15 minutes, the sun moved far enough that the shadows moved, and his system got completely lost. So here's the cart. There's 15 minutes while it's collecting the data and thinking, and 15 minutes and it's collecting the data and thinking, but it was able to make its way through this sort of blocks world kind of system. When Hans came here, we started building indoor mobile robots. This was the IMP. This one had a sonar that could look around. And keep going a little bit. So with the sonar, you can follow things. And this was my thesis work with Larry Matthews, trying to do computer vision on this vehicle, and goes, instead of 15 minutes now, it's 1 minute, and think and then move, and 1 minute and think and move. Let's go back to the slides. So that was kind of the state of the art, is a minute and think and move, and a minute and think and move. And we put together this crack team of seasoned experts. Next, oh, I've got the clicker. What did we learn? Robotics is not just AI. Vision is tough. Outdoor vision is even tougher. We built Pluto and Neptune, put together a crack team of seasoned experts. What did we learn from that? Well, we learned that speed matters. If you can process in 1 minute instead of in 15 minutes, that qualitatively changes what you're up to. We learned that teamwork matters. Takeo said, give me one idea in common of all successful computer vision systems. It wasn't hard because there weren't very many computer vision systems that were successful. He said each of them was built by one person. Well, Larry and I built a system, but we were sitting back to back in the same office. How are you going to scale this up so that you can have teams of people working on things? You have to have an architecture. We hadn't invented robot architectures yet. All of our robots had tethers. Our computers were about the size of that screen. Our robots were about this big. Tethers are a pain in the neck. We busted the hose mobile. With that background of indoor robots moving slowly, DARPA had this great idea. They had invented supercomputing, Clint Kelly showed up as the head of the office. And because they were DARPA, they had to have something for the Air Force, the pilot's associate. They had to have something for the Navy, the Naval Task Force Planner. And they had something for the Army, the Autonomous Land Vehicle. Engineering Topographics Lab ran it. We were assigned a Captain Rick Lynch from the Army, who is retired as a 3-star general, and a guy named Clint Kelly, who was the DARPA program manager, along with Bob Simpson and Ron Olander, who was Raj's first vision student, who had been a DARPA program manager. What did they want us to do? Want us to go cross-country, first of all, on roads 10 kilometers an hour, then obstacle avoidance, then cross-country, then road network planning. All of this from a basis of move, stop, with these little indoor robots. So what did we do? We put together a big team. Martin Marietta at the time, before it became Lockheed Martin. Keith is here, Rich is here from Lockmart. Hughes, the Environmental Research Institute of Michigan, and the Tech Base. This is what the autonomous land vehicle looked like. If you wanted to carry your own computers, you needed something the size of a locomotive, and the various teams of people working on it. What do I know about this? Well, Carroll Shelby of the Shelby Cobra built the chassis for this thing. The last time I saw it, Red had it and was headed up Mount Erebus carrying one of his robots to rappel into the volcano. There are a bunch of computers on there. The Butterfly had 20, count them, 20 powerful processors. The connection machine never made it on. It had gazillions of processors in a very weird folded torus method. The Warp built here was a supercomputer which would occasionally catch fire. And what did we learn from all of our work there? Well, we learned that color processing isn't always reliable. Rich was telling the story about the helpful grounds crew cut the grass. As soon as you cut the grass in Colorado in the summer, it turns brown. Everything trained on green grass now all of a sudden doesn't work so well. We learned that it's very hard to see where the rocks are hidden in the tall grass. We learned that the clouds cover the sun. It changes the illumination patterns. We learned that if you have a small error and a bigger error and a bigger error, pretty soon you are feet off of the road. We learned that the complicated architectures we developed didn't always work in the real world. And we learned that teamwork is all of the above. We also learned that road shapes aren't always reliable. A group, not us, said, well, okay, if the road shape looks like this, what does that mean? The road is curving up, right? So that's good. Now you can plan in 3D what the vehicle is up to. If the road looks like this, what does that mean? Well, you're coming to the crest of a hill and you can plan in 3D what the road is doing. What if the road looks like this? Well, at the bottom, the road is going along straight. Then it's actually the edge of a pothole, but it looks like you've just fallen off of the edge of the world. Then it looks like it's going straight again. And what happens at the top? The only geometric explanation is that the road must be folding back on top of itself. Now, the vehicle itself ran along the 2D projection of this 3D path. When it hit that inflection point, it turned around and headed backwards. If you're walking behind this vehicle with a kill switch and a 20-ton vehicle turns around and heads straight back at you, it can be a life-changing experience. So we said, if we're going to play in this game, we better have a vehicle of our own. And fortunately, Red was building the Terragator. Go ahead and flip back to the video. And the Terragator was a very simple vehicle, but very rugged, and was able to run in all kinds of different places. We ran it outdoors on the path. Why don't you click ahead to the next segment a little bit further? Yeah, right there. We ran it in a coal mine using the sonars built by Alberto Elfez. And then Red's group built the Nav Lab, which my group got to play with. This was a game changer. With the Nav Lab, you don't see any tether. For the first time, we had onboard computers, we had onboard sensors, we had onboard power, and very importantly, we had onboard graduate students. You'd be surprised how much the quality of the code increases when the graduate students are going to be the first at the scene of the accident. Let's flip back to the slides. So this, again, was a real team effort just to build these vehicles. Good. This is one red, you could tell why he was called Red. He still had red hair. The group who were building the interrogator. And what did we learn from that? We learned that really building a capable outdoor vehicle back then had to be big just to carry all of the computing. We learned that things like coal mines, which we thought were going to be difficult, were easy. Nice rough edges, the sonar bounces off of it, comes back at you. All of the work we had done going down halls, you have a nice smooth hallway, the sonar hits the hallway, it bounces off, it never comes back. Now all of a sudden you can see things. So things that we thought were going to be hard turned out to be easy. Learned that simple is good, and we built the nav lab. What did we learn from the nav lab? Well, having everything on board is critical. Now you can go any place that you want. We learned that no one vision approach was perfect. Kevin, you just missed the picture of you. We had multiple different ways of seeing the road, signal processing based, shape based, neural net based. And I found that it was a good idea to hang out with smart people. There was this French postdoc named Hebert that showed up. And I would tell my students, if you have a really difficult question, my office door is open, come see me, we'll go ask Marshall. And we hung out with a guy named Hinton, who knew a thing or two about neural nets. So those were all important. What else did we learn? Lots of different sensors. Takeo built 3-eyed cameras, 4-eyed cameras. Dirk built a radar, played with we had such an early laser rangefinder, the company that built it didn't have a way to look at the images. They were delighted when Marshall sent them images. Oh, that's what we're seeing with the thing. Sonar, Dirk did first autonomous parallel parking using sonar. Speed matters hugely. If the sun going behind a cloud is an instantaneous event, all of your colors have changed. If it's a gradual event because you're processing fast enough, now you can keep up with it with your image processing. If you've got maps, use them. And you're going to have multiple coordinate systems, one for reactivity to not run into something, one for planning. And that means that somebody had better invent SLAM. We didn't know what it was, but we knew that somebody better do it. NavLab 2 took us to the next level, both in terms of off-road capability and in terms of speed capability. Go back and show a little bit more of the video, if you could, please. NavLab 2 with Alan Alda was out running around on the slag heap, and I got this panicked phone call saying we had to abandon the run. There's a wild bear on the slag heap. Things that you wouldn't expect. So there's the NavLab 2 going down the road. And can you click, see what else we've got to show here? There's Dean doing the first run up to Erie. There's Tony's cross-country path planning, et cetera, et cetera, et cetera. Okay, let's go back to the slides. Thank you. So what have we learned from all of this? Well, it turns out we were working really hard to go up the path in Shenley Park. Road following at highway speeds was a whole lot easier. Why? Because roads are designed to be driven at highway speeds. They have lines painted on them. So some of the things we thought were going to be hard turned out to be a lot easier than we thought. Human-robot interaction, Jenny Kay was doing teleoperation of a full-scale Humvee. That can be exciting if you need to have a kill switch near you. We learned that trying to drive on dirt roads is a whole lot harder than trying to drive on paved roads. They don't have paved lines, but the crew figured out how to mix those two together. We figured out if you have Alan Alda around, look out for bears. We showed up at a DARPA program meeting to show our video of Alan Alda riding on the vehicle, and 3 other people showed up with their videos of Alan Alda and their robots. So what did we really learn? We learned that it was possible to do outdoor autonomous navigation. There was no one technical key. It was a lot of hard work by a lot of people that came together. I claim that perception is still the hard part. Yes, it's important to have an architecture. Yes, it's important to have a planner. Yes, it's important to build SLAM, but if you can't see, you're going to have trouble. You can see better if you have better sensors. You can see better if you have better computing. You don't have to see better if you have bigger wheels and you can go over bigger bumps. Better architectures can help. Really trying to figure out how to close the loop at high speed with vision was important. Better vehicles can help. During the course of this, I collected my favorite quotes, some of which have nothing to do with anything technical, but here's what I remember from this. Intelligent robot is a half a dozen expert systems and a gorilla. The point being, at that era, we were pretty good at doing symbolic reasoning, but the gorilla, the perception, the mobility was still the tough part. That's Scott Fallman. Simulation is doomed to succeed. That's Rod Brooks. You can simulate all you want until you take it out and you encounter the real world. You don't know what you're going to be in for. Our DARPA program manager, Eric Matella. Professor Kanade, have you ever been shot at? Takeo looked completely taken aback. Red laughed. Every robot I ever built has drawn blood. Red Whitaker. These are big robots. They're out there doing big things. They can hurt you if you don't take care. Finally, the reason I got involved in this, 40 years ago, I defended my thesis. I thought I was going to have some time off to decide what to do. Raj shook my hand. He said, congratulations. What you should do is start the NavLab project. Every major step in my career since then has been Raj saying, what you should do is take over as director of the Institute. What you should do is go to Qatar. So now it's my turn to say, what you should do is applaud Raj and thank him for all of the work he did in getting us started. Thank you, Raj. We had invited Clint Kelly to show up and give a talk. Clint is unable to travel right now. Clint, most of you know as the person who funded the early NavLab work, and indeed, if you read his official bios, he is most proud of his contributions to the autonomous land vehicle. Prior to that, he was a naval officer. After his stint at DARPA, he went on to be a very successful technology vice president of major aerospace companies. What you may not know, sitting on my coffee table at home, is this wonderful picture atlas of all the world's penguins. Clint's hobby was going around. There are 20 species of penguins, some of whom only live on islands in the South Pacific visited once a year by a tramp freighter. And he hoped that the day the freighter visited, it was sunny so he could get pictures. So he wrote the definitive book on all the world's penguins. And most recently, within the last couple of years, he's become an astronaut. It turns out when he went up into space, 2 of the engineers on that came up to him and said, Dr. Kelly, we were members of the rocketry club at University of Louisville that you funded. Thank you for funding. It's because of your funding that we were able to do this today. So in his absence, I would like to say the same thing. Thank you to Clint Kelly for his funding. It's because of his funding that we were able to do what we've been doing today. Let's roll the video. Thank you.
Good morning. Chuck has talked to you about the past when much of what you do today was starting. I'm going to speak about the future. Let's pretend it's 2050. You've solved all the problems with autonomous vehicle navigation. Fewer people own cars. Why buy something to sit unused most of the day when you can get transportation in minutes anywhere you need to go? You also know you've succeeded because there are fewer lawsuits. The lawyers have gone off to better pastures. Parking garages are being turned into housing and repurposed for commercial use. Some of you are now developing machines for the new frontier, for use in cislunar space. When my ancestors first came to this continent, the new frontier was roughly 100 miles west of the Atlantic coast. Now it begins about 100 miles overhead. I've been there briefly, and for those of you who need reassurance, let me assure you that the Earth still is round. What will you be doing in 25 years? Developing autonomous machinery for lunar ice mining, autonomous manufactories for use in near space that take advantage of microgravity, pure vacuum, and energy, and autonomous prospectors to seek out asteroids with metals, organics, and water. Why do this? To continue to improve the quality of life for us down here on Earth, and in particular for the less developed economies without the environmental costs of exclusively using Earth-sourced resources. This future is real, not fantasy. You'll be part of it. There are business plans. This is one of them. The business case for lunar ice mining by George Sowers of the Colorado School of Mines. You can get it online. It's extremely well reasoned and makes a very compelling case for going after that lunar ice. This is my pet rock. It came from an asteroid, and it is very heavy because it is almost 100% pure iron. We have a satellite right now en route to one of these metal asteroids. Imagine a body that's 100 meters across, and it's made strictly of iron with a few other metals thrown in, cobalt, platinum group metals, and so forth.
Yeah.
So there's a lot of resources in space, in cislunar space, but it's not a very good place for a lot of humans. And that's why the autonomous systems that you will build will be in extraordinary demand. It's going to be a while before this develops fully, although there are a lot of business plans out there, a lot of new startups, and a lot of venture money. But it wouldn't hurt if you began to read a bit about what's going on today to prepare yourself to participate in a few years. Sorry again that I can't be with you, but there is one in the audience with you who has thought a lot about these issues. I've had the pleasure of working with him on a couple of the DARPA Grand Challenges and some other activities. His name is Red Whitaker. So take advantage of his presence, talk to him about the new frontier. Hope you have a great rest of the conference. Go for it. Ad Astra.